Hi, welcome to the fourth part of our lecture entitled More on Triple Integrals in Rectangular Coordinates. So let's have a more challenging example here. So the question is to rewrite the triple integral. So we have this triple integral, okay, such that the partial integration is performed in the following order. So dz, dy, dx. So the given has dx, dz, dy, and we want to write it in dz, dy, dx. So I think this is reminiscent of what we've done before, which is to switch the order of integration. And you remember that in double integrals, in switching the order of integration, it is not just it is not simply to switch the integrals, right? Because the limits of integration will more likely than not they will change. Okay. So very important here is your ability to draw and imagine the solid as you draw the solid. Okay. So actually there is in the original slides there is a drawing here, but I want to draw it myself here so that you get the thinking process of how it is drawn. So first, let's establish what kind of solid this triple integral came from. So remember, we know that we know what type of solid uh, by looking at the innermost integral. Because the innermost integral is integrating with respect to x, that means that the region over here is a region in the yz plane. So that means this is a solid. So this is a solid of type YZ. Okay? And again, what are solids of type YZ? These are solids wherein the projection is on the YZ plane or in the YZ plane, and then there is well-defined roof and floor functions. So what we can do is first establish the limits of integration of each variable. So you have x is between 0 to root z, z is between 0 to 4 minus y, and y is between 0 and 4. So I'm going to draw here the coordinate axes. So remember that this is x, this is y, and this is z. What is the first thing that I should draw? The first thing that I should draw is the projection of the solid onto the YZ plane because this is a solid of type YZ. So I'm just gonna focus my attention to these two limits of I mean two variables with their respective limits of integration. So here y is between 0 and 4, and then z is between 0 and 4 minus y. So remember that z equals 4 minus y, you can rewrite that as y plus z equals 4. So y plus z equals 4, what is that? It's a line, no? It's a line on the yz plane whose intercepts are all 4. So you have this. So you get this triangle. So that is your R here. This is your projection. Because remember, Z is between 0 and y minus 4. Sorry, 4 minus y. And then y ranges from 0 to 4. So now the first step has been done. We have established what is the projection onto the YZ plane. Let's now establish the ceiling and the floor functions. So the ceiling and the floor functions can be found in the first equation. So this is the first equation. So clearly the floor function is the first part of the inequality 0 equals x. This is the floor function. And the ceiling function will be x equals square root of z. This is the ceiling function. Or sometimes maybe it's better to write it as z equals x squared. So x equals 0 is nothing but the yz plane. So that is already your floor function. Now we just know we just find out what is the ceiling function, no? So remember that this is the floor function, and the increasing direction is going to this direction, no? The arrow is through the it is along along the increasing direction. Okay, so now the floor function is already okay. Now let's draw z equals x squared. So this is again a cylinder with the variable y as absent. So what you can do is so draw this on the xz plane and then propagate it along the y-axis. So z equals x squared is just a parabola. So I'm just gonna draw the parabola on a different color. So maybe something like that. And then you propagate it along the axis of the missing variable, which is y. So that's say something like that, and then like that. Okay. So that is your ceiling function, right? So can you now imagine the solid? So it is the solid whose projection is this triangle R, whose floor function is the YZ plane itself, and then the ceiling function is this parabolic cylinder Z equals x squared. So maybe let's just draw those lines that will now make clearer the solid. So I'm just gonna put here something that is parallel to the x-axis, and then I draw here this curve. So I hope that is clear to you. Uh-huh. So this is what you get. This is what you get from the top. So this is the top view of the solid, and then from the side, then you get this parabolic cylinder, and that's it. Okay, so that is how you draw the solid. Okay, so in the next slide, we'll have a more a better drawing of the solid as well as the region R. So this is the solid here. So does it look the same? I hope it looks the same. Okay. So now so G I just rewrite this part to like this one, okay? So uh so we have this solid which is redrawn here with with technology, and we have this region. Okay, what was the problem again? The problem is you want to rewrite this integral with dv replaced with dz dy dx. Okay, so that means that you will be integrating with respect to z first, and that means that the projection will be onto the xy plane. So we are treating this as a solid of type xy. Okay, so so how is this a solid of type xy? So we have so the question now is, do we have a projection onto the xy plane? And after getting the projection onto the xy plane, is it clear that throughout all the points of that projection you can find definite ceiling functions and floor functions? And the answer is yes. So if you project, no, if you project onto the xy plane, what you get is this parabola. I hope you can see it. Okay. So and the floor function will be the parabolic cylinder, and the ceiling function will be the plane. So I hope you can see that, right? So let's start our analysis. So first, how do you get the equation of the boundaries of the projection onto the xy plane? So let's first project this onto the xy plane. So again, this curve is the curve of intersection of these two surfaces, and we want a projection onto the xy plane. What does that mean? We want to eliminate the z variable. So how do you do that? So you just simply uh, solve for z here and then substitute it to this variable. So if you solve for z, you get z equals x squared. That's clear. And then therefore, instead of writing z here, we just write x squared. So y plus x squared equals 4 would be the equation of this parabola over here. Okay. So maybe I write it here. So you have uh, this one satisfies. So this one satisfies y plus x squared equals 4. So y plus x squared equals 4 is y equals 4 minus x squared. And how does that look like? So you have a parabola opening downwards, still in the first quadrant because we are in the first octant. Therefore, the projection will still be in the first quadrant. So this would be 2 and this would be 4. And this is your projection onto the xy plane. Onto xy plane. Okay? So now, after getting the projection onto the xy plane, we find the limits of integration of our elevation variable, which is z. And as I've told you before, it's clear that the floor function is the blue surface or the parabolic cylinder, which has equation. What is the equation of the parabol? Ah, it's here. The parabolic cylinder has equation z equals x squared. I hope you get that because I just squared both sides. And then the ceiling function will just be the yellow surface, which has equation z equals 4 minus y. So this would be the limits of integration of the innermost integral and the double integral. The limits of integration of the double integral will be found by considering this region with boundary lines and parabola. So let's redraw that here. So here I've redrawn what I drew before. So again, you have y equals 4 minus x squared, you have x equals 0 and y equals 0. And so you see, if you treat this as, so remember what we want is, we want dy dx. That means that we will treat R as a type 1 region. So we look at the vertical strip. The bottom function is y equals 0. The top function is y equals 4 minus x squared, and it's clear that it's in the second integral, the limits of integration of the second integral, and the x here ranges from 0 to 2, so you have that one. And then I said before that the limits of integration of z are x squared and 4 minus y. So you can see it from here. So after plugging in those limits of integration, we found our answer. Okay.